Hello. Forgive the stuffiness, I'm a little under the weather today. So I'm going to skip ahead a little bit to chapter 16, talking about the interaction of lipid and carbohydrate metabolism. So you might notice that in this presentation there's some extra slides, more than just are posted from ACSM. So I added some of my original work in here to help explain things better. So traditionally we have what we call the classic carbohydrate fatty acid interaction studies, and this started off back in like the 60s with Randall. So what he did is he looked at fuel selection in both cardiac tissue and diaphragm muscles from rodents and kind of overloaded with one fuel or the other, and he found that when you did that, when you put a lot of carbs, you don't burn fat. When you put a lot of fat, you inhibit carbohydrate oxidation. So that started the dawn of what we call the Randall cycle. So kind of in a nutshell is what I just said. When you increase fatty acid, you're going to end up kind of overloading the mitochondria, and you're going to have things like citrate, increased citrate. You'll see at the bottom. Here's my cursor. The citrate is going to inhibit phosphofructokinase. So when this happens, you're going to have a reduction in glycolysis. And so overloading the system with fat will reduce glycolysis. But on the flip side, putting a lot of glucose in place will also inhibit fatty acid oxidation. So a little more detail is you don't really burn glucose in glycolysis. You actually burn G6P. So it's glucose 6-phosphate. In order to get to G6P, you have to use hexokinase. So if you have a lot of G6P present, it's actually going to have negative feedback and inhibit the hexokinase, which makes sense. Why would you make more G6P when you have a lot of it? So you reduce the hexokinase, you reduce the amount of G6P that you make, and this is also a result of increased fatty acid oxidation. So you're going to have basically a lot of acetyl-CoA coming from beta oxidation, which is going to enter into the Krebs cycle, also known as the citric acid cycle. So you also have a lot of citrate. And like I said, this kind of combination of increased fat using beta oxidation, Krebs cycle will inhibit different aspects of glycolysis, including hexokinase, phosphofructokinase. And this is all kind of basic stuff that we learned or hypothesized from Randall's work. So the original glucose fatty acid cycle was strictly based on diaphragm and cardiac muscle in rodents, but that doesn't necessarily apply to skeletal muscle. So this could be a lot larger variation in metabolic demands of skeletal muscle, which also draws on carbohydrate and lipid from different sources, mainly intramuscular and circulating. So what's not written here is also you don't have an all or nothing response to skeletal muscle. I mean, nobody ever goes from complete beta oxidation to complete glycolysis. There's a lot of shades of gray in between. So these things in mind, there's probably mechanisms in the glucose fatty acid cycle that we think of in the Randall cycle that don't apply to skeletal muscle, and things that we have never really thought of, at least back in the 60s, based on Randall's work. Luckily, it has been advanced since then. We'll look at the effects of increased plasma fatty acid on carbohydrate metabolism in skeletal muscle, human skeletal muscle. So originally, the work in the cardiac tissue did not account for glycogen phosphorylase. So we have altering substrate availability, and that changes in the intracellular environment of the skeletal muscle affect oxidation, because it's like real estate. It's location, location, location. So you're going to burn what's most available, what's nearest to the mitochondria if you are aerobic. So it can create a reciprocal relationship between carbohydrate and fat oxidation. If you have a lot of carbohydrate readily available right next to the mitochondria, that's probably what you're going to be burning. And if you start changing to have a lot more fat nearby, you're going to switch to burning fat. That being said, if you're fasting, you're burning fat, and then suddenly you say eat a meal, all right, then you're going to have a big shift in carbohydrate oxidation, shift from burning fat to carbohydrates, and it might take a little bit of time because you have mitochondria kind of overloaded with lipid at the time, so you're going to have an efflux of acylated carnitines or acylcarnitines that come out of the mitochondria so that they can switch from burning fat to burning carbohydrates. So there's a lot of in-between here. You're not going to be all or nothing, and things do change. So the shifts in the fuel oxidation between the carbs and the fat are going to depend on the activation of different enzymes like phosphorylase and phosphofructokinase and pyruvate dehydrogenase, among others. So this is one of the extra slides. Think about it, physiologically. Say after a meal, for example, about 80% of blood glucose is disposed of in skeletal muscle, but it's not a uniform finding. It's anywhere between 20 and 80%. And this is just, we're talking about a switch from fasting to postprandial. So the big disparity between the 20 and 80% could depend on two major factors. There's metabolism. Within the myocyte, you have GLUT4 translocation, and GLUT4 is the primary glucose transporter for things like skeletal muscle. And then there's also a vascular aspect. So you have macro and microvascular systems which facilitate the delivery of glucose and insulin and oxygen to the different metabolically active tissue. So the disparities that we see in substrate switching are most likely related to both of these because, let's face it, these two things control pretty much all of metabolism. So when you have a lot of plasma free fatty acid, say during cycling, during exercise, for example, what's going to happen is when you're infusing that free fatty acid, you're burning a lot of fat. And whenever you do not have the high fatty acids, like in the control, you're burning much less fat. So what's available, you're burning. And the active tissue, you're bypassing insulin at this point, and you're using a second messenger system where the calcium secreted from the working muscle activates calmodulin, which bypasses the insulin receptor and causes substrate to be uploaded into the muscle. So, like I said before, whatever's readily available is the most likely source to be used, especially during exercise, because you eliminate the need for insulin. So when you're infusing fatty acid, you can use fatty acid a lot more readily, but it's not really as simple as just that. If you look at the different levels of arterioles, you have second, third, fourth, and fifth order arterioles, and then capillaries, we have different responses under different conditions. Well, capillaries have no smooth muscle. They're just porous beds of permeable tissue for substrate exchange. So the regulation of blood flow to any tissue to the capillaries is going to be controlled by these precapillary arterioles, the third order and the fourth and fifth order arterioles. So what happens, for example, with insulin is it'll bind to the insulin receptor and phosphorylate IRS2, causing a cascade in this pathway. This is the classical pathway for insulin stimulation. You have AKT, endothelial nitric oxide synthase, which of course stimulates nitric oxide, causes vasodilation, arteries to dilate. So right here, your precapillary arterioles will dilate, allowing more blood to flow into the capillaries. So when more blood flows to the capillaries, you have more substrate delivery. However, there are times when this does not work correctly. On the right-hand side, you see the insulin still binds to the insulin receptor, but instead of IRS2, you're going to actually stimulate a completely different pathway. This is kind of mapped out by Michael J. Kwan. This is your RAS-RAF-MAP kinase pathway, and instead of nitric oxide for vasorelaxation, you have endothelin-1, which causes the opposite. It's vasoconstriction. So you reduce the amount of blood flowing to the tissue that this is happening. What this doesn't show is at the same time, this healthy pathway on the left also stimulates GLUT4 translocation. So not only are you delivering more glucose and fat and insulin to the muscle, but you're also stimulating GLUT4 much more readily. And on this side, you're inhibiting the transport of glucose. When you have the vasoconstriction, there's an adjacent pathway that blocks GLUT4 translocation, making it so that you do not actually upload the glucose. So this causes a problem with insulin resistance, and it also may help explain some of the differences we see in substrate oxidation in healthy people. So to kind of give you an overview, you've got the delivery of glucose, insulin, oxygen up here in the capillary, and then down here in the muscle. All right, this is a normal healthy cell. We have regular blood flow, nice delivery of these hormones and oxygen and substrate. You're going to bind to insulin, stimulate this nice normal pathway where GLUT4 will translocate, pull the glucose in, and you can have substrate oxidation. But there are conditions where your insulin receptors are not working properly, and this is not going to cascade in the same way. Now, on the flip side, you also have, this is muscle insulin resistance. You also have vascular insulin resistance, which precedes this. So the insulin can actually bind to insulin receptors in the vascular endothelium and cause vasodilation of the smooth muscle in a healthy environment. But in an unhealthy environment, they'll actually cause vasoconstriction and reduce the delivery of insulin and glucose and oxygen to the different tissues. Now, this is just kind of an overview of the regulation of certain enzymes in carbohydrate metabolism. So under stressful conditions like exercise, for example, you have increased epinephrine, stimulates cyclic AMP, which causes an entire cycle of glycolytic activity to occur. So you're going to increase glycolysis. On the flip side, if you have a lot of acetyl-CoA, NADH, ATP, you don't need as much glycolysis. So these things can actually inhibit something like phosphofructokinase and slow down glycolysis. An easy way to think about this would be, you have ATP, you don't need to make it, right? If you have a lot of NADH, you don't have a lot of NAD ready to grab those hydrogens, so that slows down glycolysis. And if you already have a lot of acetyl-CoA, that means you're being aerobic. You're using the Krebs cycle, the electron transport chain, so you don't have to rely as much on glycolysis. So decreased glycogenolysis, which is the breakdown of glycogen so that it can be used in its oxidized form of G6P. So decreased glycogenolysis with high fat provision may be explained by reductions in ADP, AMP, and inorganic phosphate. So if you recall from previous chapters, having a lot of ADP or AMP or phosphate stimulate PFK and stimulate glycolysis. These are signs of ATP hydrolysis. So the more ATP you use, the more glycolysis you're going to end up needing. So it'll stimulate glycolysis. But a lot of fat, you can reduce these levels of ADP, AMP, and phosphate. There is a reciprocal relationship between carbohydrate and fat oxidation during exercise, in that when one increases, the other decreases. This was originally explained by Randall. So we see that the carbohydrate and fat oxidation during exercise at submaximal powers, between 40 and 80%, can yield some different results. But increasing the availability of free fatty acids doesn't seem to have an effect on acetyl-CoA or G6P contents. But when you get to particularly high activity levels, or, like I said, I'm a little under the weather today. Intensities, that's the word. Particularly high intensities, we do see a bit of a shift. We're going to get to that a little bit later. So glycogen phosphorylase flux is a bit more dominant, around 80% of VO2, and has less of an impact submaximally. Accumulation of adenosine diphosphate, ADP or AMP, or just your free-floating inorganic phosphate, is reduced during exercise when you have increased free fatty acids. And this is potentially because the mitochondrial nicotinamide adenine dinucleotide, or your NADH, is more abundant with a high fat provision during the onset of exercise, increasing the aerobic production of ATP and reducing the mismatch between ATP use and supply. So when you're making ATP through glycolysis, you're basically getting a net of 2 ATP just by anaerobic means. When you continue that aerobically and it's converted to pyruvate, and the pyruvate becomes acetyl-CoA, that's going to go up to about 32. That's a fair amount of ATP, but when you use fat, the most abundant fat in the body is palmitate, because it's also the most abundant fat in the diet, and that's a 16 carbon fat. So when you break that down, it's going to have 7 beta oxidations, and each beta oxidation is going to lead to acetyl-CoA and produce NADH. And so when you cut to the chase and do the math, one glucose molecule will give you about 32 ATP, and one string of palmitate will give you about 129 ATP, and that's about 550% more efficient. So when you're using fat, you're making a lot more ATP, changing the ratio of ADP to ATP, and thereby slowing down phosphorofructokinase, which is the rate-limiting enzyme for glycolysis. All right, moderate exercise, long-term, 1 to 2 hours, that's going to stimulate a more robust reliance upon free fatty acid, thereby trying to spare muscle glycogen. However, something that long, you have to use the glycogen anyway, because fat burns in the flame of carbohydrates. When you break down glycogen, you make pyruvate, convert it to acetyl-CoA. That process actually gives you some important intermediaries in the Krebs cycle. And if you don't have carbs to break down, you can't make those intermediaries like oxaloacetate, and the Krebs cycle shuts down. So you have to rely more on fatty acid to make the abundance of ATP, so that you don't have to rely on glycogen for ATP. You can rely on it for a little bit of ATP, but mostly to make the intermediaries needed in the Krebs cycle. So the result is you have increased fat oxidation, decreased carbohydrate oxidation, and a decrease in PDHA. There's no change in the energy status of cells. They're still using the same amount of energy, and no decrease in pyruvate content. Since you're relying more on fat, you don't have to increase or decrease the pyruvate. So increased free fatty acid availability during prolonged exercise. You have high fat availability because you've stimulated lipolysis. That upregulates PDK activity and inhibits PDH activity. Phosphate. Now just to go back to this, when you have a high fat situation, when you have high free fatty acids, what we found a few years ago in rodent models is that infusing free fatty acids or stimulating lipolysis with heparin infusion will actually cause vascular insulin resistance, so the delivery here would be decreased. When you decrease the delivery of any kind of fuel to the muscle, that includes insulin, and insulin is going to be very important for the uptake of glucose. So just by infusing fat under just normal resting conditions, you're going to decrease glucose uptake and oxidation and increase fatty acid oxidation. There are reasons for this that we'll get into. Okay, the sources of fat for skeletal muscle are going to come from two forms. Obviously, there is the intramyocellular triglycerides and the circulating free fatty acids. That doesn't matter to the muscle which one they burn. It's basically the same composition, but typically they'll burn the ones that are closest to the mitochondria first, altering the intramyocellular triglyceride content can affect carbohydrate oxidation. And an example of this is both, it's kind of a bipolar example, really. It's look at people with type 2 diabetes as well as elite marathon runners. Both of them burn more fat than carbohydrates, and both of them have increased intramyocellular triglyceride content. Of course, one is very insulin sensitive and one's very insulin resistant, but that's a lecture for another day. A common way of altering your IMTGs is through changing your diet. So if you ingest more fat, you're going to have more fat in your muscles. But of course, like I alluded to before, there's a healthy way and an unhealthy way to do it. If you're chronically exercising, that fat will be healthy, and if you're not, it'll be unhealthy and you'll have insulin resistance. But when you do this and you change your dietary content over the course of days or weeks, you not only change the composition of the fuel in the muscle, but you also change what it burns, and that's called metabolic flexibility. So there's different ways to measure that. One of them is an acute way, where you can just take a person fasting and give them a meal and measure their whole body RER, and you can see the change in your RER. If it goes up and then comes back down quickly, it means you're going from fat to carbohydrates, back to fat again. It means you're metabolically flexible. If you're metabolically inflexible, you're burning a little bit more fat at rest anyway, and that change is much more subtle if it happens at all. So you're thought to be inflexible. Now that's the acute way. The chronic way to measure metabolic flexibility is, like I just mentioned, changing your diet. If you have a high carbohydrate diet, then at rest you're going to oxidize more carbohydrates because you'll store more carbohydrates right next to the mitochondria. You switch to having a high fat diet, and then you will switch to burning more fat. So this is a case of food quotient, or FQ, equaling RQ, or RER. So that's the ability to switch substrate oxidation upon stimulation. So when you have increased muscle glycogen availability, you can change your free fatty acid uptake, your IMTG metabolism, and even your free fatty acid oxidation. With dynamic exercise, you can increase exogenous glucose availability. All right, you inhibit fat utilization during exercise because you can decrease fat availability as a result of decreased lipolysis, which is the breakdown of triglycerides to form free fatty acids circulating the blood. And that directly affects fatty acid oxidation in the muscle, all secondary to the insulin concentrations, which will increase. So when you increase glucose availability, insulin spikes, moves glucose transporter 4, or GLUT4, to the cell membrane to move glucose in, giving you more glucose in the cell. And like I said, the whole oxidation principle is similar to real estate. It's all about location. Well, not all about location, but location is very important. All right, with increased insulin, it will move substrate into cells. It's not just glucose, but it'll move glucose and it'll move fat. So when you have increased free fatty acids, you're going to have an increase of insulin. That's going to stimulate fatty acid transport, fatty acyl-CoA, beta oxidation, acetyl-CoA production, and citrate. Now remember, citrate will also inhibit phosphofructokinase. When you have a lot of glucose, that also stimulates insulin. And insulin's going to move whatever substrate you have in the blood into storage or into oxidation, depending on where it's going. It'll move the free fatty acids into the triglycerides or into the muscle. It'll move the glucose into the muscle so that you can make G6P with hexokinase and increase your pyruvate levels, making more acetyl-CoA. Now this is an example of actually ingesting different meals. So you can have a high glucose, which is the oral glucose challenge here, or a mixed meal with mixed composition, fat, protein, carbohydrate. That's the mixed meal challenge. So they'll have a robust difference in the change in circulating blood glucose. Obviously, if you consume straight glucose, your blood glucose is going to go up a lot more, as evidenced by these different time points and the area under the curve. However, as I said, insulin, protein, glucose will all stimulate insulin. So if you look at the concentration of insulin in the body, it's pretty much the same, with a little bit of a difference over here at 2 hours after the meal. No difference in the area under the curve. And if you look at the plasma-free fatty acids, all right, fasting in 60 minutes after the mixed meal and fasting in 60 minutes after consuming glucose, there's a sharp reduction in both. So this would suggest that you have a lot more availability of glucose in the blood, the same level of insulin, and you're going to have a reduction in plasma-free fatty acid, which is going to be a surrogate measure kind of adipose tissue insulin sensitivity. So you're moving out your free fatty acids from the blood more efficiently, I would say, than the glucose, because you have so much more glucose in the blood. However, if you look at microvascular or capillary activity, this is the total volume of blood in the capillaries of skeletal muscle. This is the velocity of the blood in the capillaries of skeletal muscle, and this is the total blood flow. If you look at the blood flow in capillaries of skeletal muscle after having a normal meal, just a mixed composition, you have an increase in blood delivery to capillary beds in the skeletal muscle. So that's what you would expect. It stimulates insulin, you're going to dilate these arteries, and you're going to have increased delivery of insulin and substrate and oxygen to the skeletal muscle. However, with a high glucose load, you're going to have the exact opposite. You have a decrease in capillary blood flow to the skeletal muscle. So this is going to reduce the delivery of glucose and insulin to the muscle. It will reduce the glucose oxidation because you're not able to deliver it to the muscle as much. Now, if you look at the total blood flow to the limb, this was measured in the skeletal muscle of an arm, your total blood flow, the brachial artery blood flow, is the same between these two. So the disparity between the capillary blood flow in the skeletal muscle an hour after having a mixed meal or an hour after eating just carbohydrates doesn't change the blood flow to the limb, it changes how it's flowing through the muscle. So this is supplying glucose. At 60 minutes, it's supplying glucose to the muscle and through the capillary beds. But when you have the glucose, there's a reduction. During exercise, your exercise intensity can increase your substrate availability because you can bypass the need for things like insulin. You have intracellular metabolites that can regulate phosphorylase, pyruvate dehydrogenase. High power activities, high intensity, will stimulate kind of a stress response. Will spike cortisol and catecholamines. Your blood glucose will increase. It'll stimulate I cannot speak when I'm not feeling well. Muscle glycogenolysis, glycolytic flux, pyruvate dehydrogenase activation, and carbohydrate oxidation. So high power activities, you're going to use more carbohydrates. You're going to increase the blood glucose. You're going to increase the breakdown of glycogen because you need the ATP very quickly. While burning fat supplies a lot more ATP, it's not as fast as burning carbohydrates. So there's some mechanisms that help explain the downregulation of fat at high intensities. So the carbohydrate-induced decrease in long-chain free fatty acid transport into muscle. And I'll get into this a little bit more in the next slide. You have a decrease in intracellular triglyceride hydrolysis with high intensities. Also, the fat transport into the mitochondria is reduced. Fat transport into the mitochondria, human skeletal muscle in particular. And there are effects of pharmacologic agents on carbohydrate and fatty acid fuel selection that play a role. And also the level of training you have can help dictate if you're using more carbohydrate or fatty acid as fuel. Now, to get into this a little bit more deeply, I'm going to go kind of back in time. This is an undergrad slide, but it helps explain what happens during high-intensity exercise. So it's a stressful environment, so you're going to have increases in glucagon, epinephrine, norepinephrine, and these things are all going to stimulate cyclic AMP, which is going to stimulate hormone-sensitive lipase. So you're going to break down triglycerides into your three fatty acids and glycerol. At the same time, you're also producing lactate if you very high intensity exercises. And this will actually override all these stimuli for hormone-sensitive lipase and stimulate reesterification, in that your free fatty acids will combine back with glycerol and go back into storage. So since this arrow is drawn thick and this one's drawn much thinner, it's kind of like lactate is using a megaphone and dictating what's happening here. All these other factors are potent, but they're not as strong as the increased levels of lactate. Now, this is predominantly happening once you get past your onset of blood lactate accumulation, or OBLA, also known as anaerobic threshold. And that's 4 millimoles per liter. Once you hit 4 millimoles per liter in blood, the levels of lactate skyrocket. They go up much faster, which could help explain why it has a more potent effect on stimulating reesterification than these other factors have on stimulating hormone-sensitive lipase. There's a really great review that came out this year about the effects of lactate on the body, and I can't remember the title, but it's not going to be hard to find if you check it out on PubMed, and I recommend that. Okay, thanks for listening.